Okay everyone, so I'm redoing that inductors presentation. I saw how bad the audio was in it in a few places, so my plan is here going forward to kind of break these presentations down into smaller pieces. So as an example, this presentation probably broken down into say 3 parts or something, so that it makes the reviewing and the fixing and things like that easier. Okay, so essentially today what we're talking about an inductor, is we're talking about a coil of wire in an electric circuit. And so far we've looked at that as a coil in a DC circuit when we looked at relays and solenoids. And when a coil's in a DC circuit, it's simply used as an electromagnet. So that means that when there's current, we know there's a magnetic field created. When there's no current, there's no magnetic field, and therefore that turning on or off the magnetic field can be used to change the state of a set of contacts, as in a relay or a magnetic contactor, or move a plunger to change the state of say a valve or some other device, or door locks on a vehicle. So we know that in this case we're working with a steady, unchanging magnetic field. And with a steady, unchanging magnetic field, we just simply are using an electromagnet in a DC circuit for that purpose. But there's no induced voltage into any additional coils, or there's no induced voltage back into the same coil itself, which is really describing something called inductance. So if you were to look at an example of a transformer in a DC circuit, because the field is steady and unchanging, there'll be no voltage induced into this secondary, such that there would be 0 volts induced into the secondary for a DC a DC transformer, if you want to think of it that way. And so when that's the case, we're really talking about Faraday's law, and how Faraday's law is stating that there has to be a changing magnetic field for voltage to be induced, and that on top of it, the rate of change of that changing field determines the magnitude of that voltage induced. But the thing we need to understand is when we have AC, when we have an AC source now and a coil, the magnetic field's changing. So if we bring another coil into the vicinity of that magnetic field, then that changing magnetic field is going to induce a voltage and current into the secondary here, and we're going to have a VAC value equal to a value that's the secondary voltage from this transformer. This is describing something called mutual induction. So when you have the magnetic field of one coil inducing a voltage and current in a secondary coil, that's called mutual induction, and that's really describing what we have going on with a transformer. But if we look at a coil on its own in an AC circuit, that coil is creating a changing magnetic field. And as it turns out, that changing magnetic field is inducing a voltage back into that coil, its own magnetic field, and instead of being called mutual induction, it's called self-induction. And that's just shortened to induction. And that's why we now call a coil in an AC circuit an inductor. Okay, so when we look at today's presentation, we're basically going to be looking at all the properties that make up a practical inductor, and how those properties determine its inductive value. And the unit for inductance is Henry. So we have Henry as indicating our value for inductance. So when we look at inductor values, we'll be looking at Henrys, microhenrys, and so on, and millihenries, all of those values. Millihenries are a popular kind of engineering prefix when it comes to 60 hertz or our power systems. So when we have an inductor in AC, it now's own magnetic field causes something called a counter EMF. So that changing magnetic field that we talked about here creates a counter EMF, and that counter EMF, or that voltage, is against the applied voltage, so it's a form of opposition resisting changes in current. And that's described by Lenz's law. So Lenz's law is describing that counter EMF. Okay? All right. So we're talking about inductance and inductors. A common form of inductor is a coil of wire, like we said. They are used in radio tuning circuits. Now, when it comes to a tuning circuit, that's indicating that it's a frequency selective component. So a resistor's opposition is the same from 0 hertz to infinite hertz. It never changes its opposition in a circuit. But when it comes to an inductor, this is an example of what we call a frequency selective load. So its value of opposition changes based on the rate of change or the frequency that it's connected to. And we did look at an example, I think, before we parted ways there last week, where I showed an example of how an inductor can be used as surge suppression in a power system to protect the load against a surge in current. Because when we have a giant change in the current applied to an inductor, it creates essentially an open circuit and prevents that current from being passed on to the load. All right. So when a magnet moves through a coil of wire, we know voltage is induced. And when a conductor moves through a magnetic field, voltage is induced. So it doesn't matter whether the conductor is moving relative to the magnetic field or vice versa. There's a voltage and current induced. And that's important because that's really part of what's being described in Faraday's law when it's saying that the flux, that is the magnetic field exposed to that conductor, must be changing, right? So we know it's got to be a changing magnetic field. And now notice how it also says it's proportional to the rate of change. And this is really, in an AC circuit, can be described by omega, or the angular velocity, or which indirectly is related to the frequency. So the higher the frequency, the higher the angular velocity. So we know that the changing magnetic field and the rate of change is important in this whole thing. And then lastly, we have what we talked about in Lenz's law, and that says that the induced voltage will be one that will oppose the voltage that's producing it. It'll oppose the source voltage. It'll oppose the voltage across that component. And as a result, it's going to be an opposing force that is essentially providing opposition that we call reactance in an AC circuit. It's a special type of opposition. It's not resistance. It doesn't do real work. But it's a type of opposition in the circuit that opposes changes in current. So, as we said too at the beginning, if we have a constant current applied to an inductor, no voltage is induced. If the current is increased, that means there's going to be a change in current. And as a result, the polarity created from the reactance of that inductor is going to be one that opposes that increase. And if you look at decreasing, it's the same way. So at the end of the day, we make an overall statement that says that inductors oppose changes in current. Okay? When we look at a capacitor, we'll see how it opposes changes in voltage. Okay, so the voltage induced in a coil is proportional to the rate of change of the current. The proportional constant is L, the self-inductance of the coil. So when we're representing coils in schematics, we label them L, and L value is a value in henries indicating its inductance. So if we look down here, based on the statements we made, we have an equation that says the voltage, right, VL, or essentially what's describing the counter EMF from that coil, is the result of its L value in henries. So this will be a value in henries. And then we have our value of delta I, our change in current, over delta T. So if we have large changes in current over short changes in time, that's going to be a large delta I over a small delta T, which we know is going to result in a large number and give us greater voltage. So it's directly proportional to the change in current and inversely proportional to the change in time. So the smaller the change in time, or the higher the rate of change, the more the voltage will be. All right. So now if we look at the inductance equation. Now, I notice in the slides here, for whatever reason, when I show them here on this app, it's missed part of this equation. I'm just going to add it here now. On the bottom of this equation, I'm going to put L. L is the length of the coil in meters. So we're going to go through this equation with each variable expressed. So first of all, we said that L is in henries, right? So we know that the result of doing this multiplication and division with these units applied is going to give us henries in the end. So we're always going to be working with henries as a value of L. Now, first thing to understand is when it comes to the length, notice how the length is inversely proportional for this inductance value. The thing we need to understand is people often think that the length here is talking about the length of the conductor that makes up the coil, but that's not actually right. What it is if I look at 5 turns of a coil, this is what's called the length of that coil. It's the length of the actual coil of wire. Whereas if I look at one with 5 turns that's wrapped like that, the length is much less, right? So with the length being much less in this example, this is going to have more L value. And sorry, I'm not great with this pen here, but it's going to have more L value, okay? And so this is an inverse relationship with length. So the larger the length, the smaller the L value. The smaller the length, the larger the L value. So that's coming from this component right here. A is the cross-sectional area. So it means if you're looking down at the top of the coil, that would be an example of a cross-sectional area compared to this. And you can see that here, with a much larger cross-sectional area, every turn of the coil is going to have more effect because there's more parallel surfaces to create an increased magnetic field here. So we have a direct relationship with the area. Okay, now the next one is the number of turns. Notice how it's a squared value. So it's going to be essentially the most significant part of this equation, and doubling the turns would give you 4 times the value, tripling the turns, 9 times the value, and so on. So it's the number of turns in the coil. Okay, the last one is called the permeability. That's the magnetic properties of the core. What's in the middle of this coil? So if I think of what's directly in the middle of there, is there air? And if there's air, there's a permeability component to air. Is there iron? And then there'd be a permeability component to iron, or ferrite type materials. Okay, I know this is pretty messy, but we'll make do. Now, if we look at the picture that we have on the lower right-hand side here, if we look at the example here, we have a coil of wire wrapped over that tube, and then you can see here the core has been removed. So right there, that's what's called a ferrite core. And notice how it's threaded. So essentially what this is doing is this is making a variable inductor, right? So now we have a variable inductor here. And what it means is by threading this core into the center of this coil, by turning it, we're moving the core back and forth in there, and as a result, we will be changing the value of L based on changing the value of mu. So we're affecting the value of mu in that equation, and that's the most practical way of making a variable inductor. If I move the ferrite core right into the center, so you've got maximum coupling between the coil and the core, is when the mu value will be the highest, and therefore the L value will be the highest. Okay, so we'll just end off here for part one. So this again is saying that when we look at a changing current over time, the more the current changes with respect to time, the higher that voltage will be, or the higher the counter EMF. And that's really how come when we're looking at something we're going to look at later called the reactance of this coil, symbolized by XL, we have XL equaling omega L, and the more the higher rate of change we have in this equation, the higher amount of opposition is going to come from XL. So it's all related to. Okay, this is part two of that presentation on inductors. So this is where we look at inductors in series and in parallel, and the combination of, to determine a total value of inductance, which, don't forget, is in the units henries. So L total is a total Henry value or inductor value for these connections. Now you'll find these formulas on your formula sheet. So if you find the section on inductors on your formula sheet, you'll see that it says inductors in series. This is the way you come up with the total value. In parallel, and then of course you just need to know how to apply it to combinations. So to start off with here, then we have inductors in series, and the total value is just found by adding them all together. So if we take an example of some millihenry values here of L1 as 10 millihenries, and we look at L2 as 20 millihenries, L3 is 30, the result is simply adding them together, and your L total value is going to be 60 millihenries. So that's straightforward. I won't spend as much time on this. You can review this by investigating online, looking in your textbook, or simply just understanding this basic equations that we're familiar with, and then practicing it when you do that assignment that I have online here. What about in parallel? Well, in parallel, some of the reciprocals, of course, and an equation that you're used to for resistance. And notice how inductors in parallel and in series follow those same relationships or equations. Don't forget here, of course, product over sum can be used when you only have two, or you want to use product over sum in multiple steps to get the answer. So product over sum would work here as well. When it comes to the schematic symbols for inductors, there's not just the air core inductor like what we've shown in our schematics. You can have ferrite cores, which you see up here as a dotted line, an iron core, which is a more pure iron material with a solid line, and then of course you have your typical variable schematic symbol we're used to with the arrow and the line in it indicating that it's variable. Okay, so we just want to talk about inductance in DC or steady state, because as we go forward we're going to see we have a steady state equivalent for an inductor or a steady state equivalent for a capacitor, and that's really saying to DC what's the equivalent opposition of a coil of wire. And because we're looking at essentially a coil of wire with little to no resistance, the way we describe an inductor in steady state is a short circuit. And that's because the only resistance we have is the small resistance of the coil, and to DC we would call a steady state equivalent of an inductor a short circuit. Of course, you can probably imagine when we look at a capacitor, instead of its steady state equivalent being a short circuit, we're going to find that it's an open circuit. Okay? Now, just want to talk about practical inductors for a moment, and that is when we look at a practical coil or a practical inductor, just like we had a practical source or a practical conductor in a circuit where we had to consider values that are beyond its ideal values, it's the same when it comes to a coil. So for an ideal coil, the only quantity we need to deal with is its L value, right? So here's an ideal coil on top. The only thing we have to deal with is that value in henries. But in reality, any of these coils actually have resistance. A small amount, but they have resistance. So really, when it comes to a practical coil, we need to understand that it is a R coil value, right? And an L coil value, of which we usually use the series model of showing R coil in series with our L value. When it comes to the DC equivalent, which we just talked about, the steady state though, the only thing we have to consider is the R coil value here. There's no L value that we need to concern ourselves with. And we talked about that previously, and that was simply because the magnetic field's not changing, so the inductance value or the L value doesn't exist in that scenario. When it comes to an AC scenario, then we need to understand that L value does exist, but so does the R coil, or the resistance of the coil, exist when we look at the practical example. Okay? So that's what we're talking about there. So whenever we look at questions, they'll be quite specific as to say we're working with an ideal coil or a practical coil. And if we're working with a practical coil, we have to be aware of the resistance. Okay, so inductive power, we want to talk about that for a moment. When it comes to an inductor, it doesn't do any real work. We have a building and collapsing magnetic field that essentially induces energy back into the circuit on alternate cycles of the AC waveform. So what it means is that there's never any real work being done, but we need to be able to explain the voltage and the current that we have from an inductor. And as it turns out, this is something we call reactive power. And sure enough, it's also referred to as imaginary power because it's plotted on the imaginary number line. It's not doing any real work. It can't be translated to horsepower, BTU, or watts. And so it's something we call reactive power. We'll be looking at it more when we look at power triangles later on and understanding how total power is the result of real and reactive power. But when we do, then that'll make more sense. But there's no doubt the reactive power will be plotted on the imaginary number line as a plus or minus J component. Okay, last part here is just saying when you're working with inductors in the lab or anywhere else, you can really, for the most part, get a good sort of prediction if you have a working inductor by using an ohm meter. Because it's just a coil of wire, if you measure it and you have a small amount of resistance, you can be relatively sure you're working with an operational inductor. And of course, what's the most common fault for an inductor is that the power that's being dissipated by the conductor that makes up the coil can't handle it, and you end up with an open. And that would have obviously infinite resistance. So you would just connect an ohm meter, making sure, of course, the inductor has been removed from any power source, like we know we need to do when we measure resistance, and then just use an ohm meter to measure the resistance of the coil and determine a value, which is typically going to be a very, very low value. Okay, so that's all there is for that presentation. Hopefully this audio will be fixed now, and you guys can do that little practice exercise I provided on inductor